Welcome to class number 9, session number 4. In this session, we will deal with sensors that are based on polymeric nanostructures for gas sensing applications. One of the gas sensing strategies with polymeric nanostructures integrates molecularly imprinted polymers with surface-enhanced Raman scattering. Molecular imprinting involves arranging polymerizable functional monomers around a template, followed by polymerization and template removal. Molecularly imprinted polymers can be utilized as artificial recognition elements for targeting chemical analytes of interest, and there are numerous reports detailing the use of this technique for the preparation of polymers which have the ability to bind a specific chemical target. In chemical sensing applications, a molecularly imprinted polymer alone does not meet the requirements for the sensor without some form of a transducer to convert the analyte interaction into a measurable signal. One way to get around this limitation is to use surface-enhanced Raman scattering as transduction method to achieve a high level of selectivity. In the presented example on the screen, the sensor is developed to detect the explosive TNT. In this case, micrometer-thick film of salt gel-derived xerogels are deposited on enhanced Raman scattering surface as the sensing layer. Xerogels are molecularly imprinted for TNT using non-covalent interactions with the polymer matrix. Binding the TNT within the polymer matrix results in a unique surface-enhanced Raman scattering bands, which allow for detection and identification of the molecule in the molecularly imprinted polymers. As seen in the right figure, the polymer background does not prohibit TNT detection. Furthermore, the successful measurement of the TNT template within the molecularly imprinted polymers shows it is possible to develop a thin and porous molecularly imprinted polymers film which allows analyte measurement within the critical surface, enhancing field distance from the underlying substrate. The right figure shows that the response profile from TNT responsive and control xerogel films to increasing concentrations of the TNT. As opposed to the other more complicated processes to create non-structured polymers and sensors, polycyclic aromatic hydrocarbons, which we will abbreviate from now on as PAH, are excellent example of an organic material spontaneously self-assembled into nanostructures, saving both money and effort. The unique structure of the PAH molecule, which is consisted from aromatic core and organic, are mostly aliphatic side chains. These molecules provide the ability to self-assembly or self-organize into columnar nanostructures when they are drop-casted or spin-coated or spray-coated from a solution on top of a substrate. An illustration of the columnar structure can be seen in the upper right figure. Thanks to their aromatic core, PAH transfer charged carriers throughout the pi-pi connection from one side of the column to the other depending on the voltage applied, while the side groups serve as interaction layer between the charge transferring channel and the environment. The great advantage of this PAH material is the ability to create different derivatives of the PAH with various core structures and side groups, which can be basically either polar or non-polar groups, and therefore this controls the sensing abilities of the material and its conductance properties. In this case, a small change of the molecular chemistry can have a great effect on the conductance, morphology, and the interaction with the environment of the layer. In the bottom right of the screen, we can see a SEM figure of one PAH derivative on top of a silicon wafer, as well as a snail-like pathways connecting between the electrodes submerged into the silicon. The classic approach to quantify the interaction of the sensing layer with its environment is with the help of the chemoresistor device. In the example shown on the screen, cross-reactive array of well-designed PAH and single-walled carbon nanotube bilayers are constructed for sensing applications. The conductive layer of the single-walled carbon nanotube is drop-casted on the electrodes and coated with a different derivative of PAH molecules that were presented in the previous slide. In the presented example on the screen, 7 different sensors are created, where the different sensors distinguish from each the other by the type of the PAH coating the single-wall carbon nanotube layer. An illustration of the structure of the sensors can be seen in the scheme on the left, on the current screen. In the same side, you can see a SEM micrograph of the single-walled carbon nanotube drop casted between the 2 adjacent electrodes, as well as a SEM micrograph of PAH number 1, which was presented in the previous slide, coated on top of the single-wall carbon nanotubes. For details on the PAH1 structure, please refer to the previous slide. Using appropriate combinations of PAH and single-wall carbon nanotube sensors, high sensitivity and highly accurate values can be obtained for discriminating polar and nonpolar VOCs, namely volatile organic compounds, in samples with variable humidity levels that range between 5 to 80% relative humidity. The same array of sensors exhibits self-learning capabilities that facilitated exchanging information about the environmental properties and their observations. In the middle figure, you can see sensor response to successive concentrations of hexanol diluted in synthetic dry air, octane diluted in both dry air and highly humid airflow, and the response to 80% relative humidity. The red curve in the figure shows response acquired by the pristine single-wall carbon nanotube sensor. The black curve in the figure shows response acquired by the PAH4 functionalized single-wall carbon nanotube sensors. 2 repetitions were made to each concentration, and you can see that the addition of the PAH sensing layer greatly improves the sensing ability of each sensor and the array as a whole. In the right figure that is presented on the screen, you can see image plot of the sensitivity values calculated from the pristine single-wall carbon nanotubes and the PAH single-wall carbon nanotube bilayers upon exposure to various volatile organic compounds at different concentrations and background humidity. As seen in the figure, each point in these plots is an average of 3 independent exposures from 3 duplicated sensors. From the figure, one can see that although the incorporation of the PAH slightly increased the sensitivity to humidity, it substantially improved the sensing signals towards part or all of the tested volatile organic compounds as compared to the pristine single-walled carbon nanotubes. The higher the volatile organic compound concentration, the higher detection improvement. In many cases, the higher the relative humidity in the mixture, the higher the improvement as compared for the pristine single-walled carbon nanotubes. In some cases, such as for the PAH5 and single-wall carbon nanotube sensor, The sensitivity to the polar volatile organic compounds, such as in the cases of ethylbenzene and ethanol, increase with the increase in the relative humidity. This is indicated by the enhanced color variation when volatile organic compound concentrations are increased in a background of 80% relative humidity compared to the 5% relative humidity. Among all individual sensors, PaH1 and single-wall carbon nanotube bilayers, or PaH4 and single-wall carbon nanotubes bilayer, or PaH6 or single-wall carbon nanotube bilayers exhibited maximum discrimination accuracy, showing the importance of the chemistry nature of the PaH on the sensing properties of these structures. Another way to utilize the sensing properties of PaH films is by two transduction techniques, namely ellipsometry and quartz crystal microbalance. Before we proceed with the results of the sensing properties in these approaches, let's recall the basic operation mode of these techniques. We will start first with the spectroscopic ellipsometry. Spectroscopic ellipsometry is an optical technique used for studying dielectric properties and changes in thin film thicknesses. These properties are calculated from the measurement of changes in the polarization of the light that is reflected from the analyzed sample. The second technique, which is the quartz crystal microbalance, is a piezoelectric mass sensing device that has the ability to measure small mass changes down to a fraction of monolayer or a single layer of atoms. Quartz crystal microbalance evaluates basically a mass per unit area by measuring the changes in frequency of a quartz crystal resonator that is disrupted by addition or removal of a small mass at the surface of the acoustic resonator. The relationship between the change in mass and change in frequency is described by the Sorbery's equation. Using these two techniques, sensing measurements can be carried out upon exposure to various analytes. The results can be seen in the following slides. The sensor quality is studied throughout the monitoring of the changes in the physical optical properties of thin PaH film upon exposure to nonpolar and polar analytes or volatile organic compounds by means of a quartz crystal microbalance and spectroscopic ellipsometry measurements. Panel A of the presented figure shows thickness changes of the PaH film measured by spectroscopic ellipsometry upon exposure to various polar and nonpolar analytes in the presence of different humidity contents. Panel B on the screen shows changes in the frequency of a quartz crystal microbalance that is disrupted by the addition or removal of a small mass. Of course, this is done for wide variety of concentrations of polar and nonpolar analytes in the presence also of different humidity contents. As seen in the figure, for polymer film of PaH number 6, which was described in the previous slide, a definite behavior of the layer cannot be observed except for the extreme sensitivity of the layer to humidity. On the other hand, and as will be seen in the next slide, modifications of the structure of the PaH result in completely different and more promising results. Indeed, changing the sensing layer from PaH6 to PaH7, meaning changing the shape of the corona from 60 carbon number and triangle shape, and side chain characteristics, enable excellent sensitivity to nonpolar analytes compared to polar analytes in a setting of 5 to 40% counteracting relative humidity. This could be related to the interaction between the nonpolar analytes with the hydrophobic part of the examined PaH. This is most important result as nonpolar analytes are usually more difficult and more challenging to detect than polar molecules. Another popular device for chemical gas sensing is the field effect transistor. In this approach, an array of field effect transistors are constructed of 4 kinds of sensing layers based on 4 different pH molecules without any semiconductive single-wall carbon nanotube layer, as we have seen and presented in the previous slides. The structure of the field effect transistor can be seen above. A modification of silicon oxide was created silane layer, whose purpose is to minimize the hysteresis effect of the various humidity levels present in the experiment, which are presented on the screen. The advantage of using a field effect transistor is by extracting multiple non-dependent electrical features, namely increasing the amount of information regarding the interaction between the layer and gas analyte. In the present example, 4 electrical features are extracted from each sensor. The features that are extracted from the current versus voltage curve seen in the right figure are hole mobility, voltage threshold, on-off ratio, and the current at a specific gate voltage, in this case at -20 volt. An example of the exposure of these pH-based field effect transistors to ethylbenzene and extraction of the normalized voltage threshold feature from each exposure can be seen on the slide. In this case, the R0 is an average of 5 measurements at the end of air exposure step, and the R1 is an average of 5 measurements at the end of an analyte exposure step. The same process was conducted regarding all the exposures and all other electrical features of the pH-based field effect transistors have been carried out. Some of the results of the pH-based field effect transistors are presented here. In the left side figure, you can see the normalized mobility values in 5% and 40% relative humidity. When proceeding to extract the data from all of the features and sensors, a very large amount of information is received, and therefore a statistical analysis is needed to organize the information and to understand the value of the results. Since that is so, discriminant factor analysis is applied in order to evaluate the abilities of the array to separate between the different groups of the analytes. Please note that the discriminant factor analysis method effectively reduces the multidimensional experimental data, and the classification success accuracy is estimated throughout the leave one out cross-validation. In the right side figure, on the screen, you can see discriminant factor analysis results separating the non-aromatic, namely octanol, decanol, hexane, octane, decan, and aromatic analytes, basically mesitylene, styrene, ethylbenzene, and toluene. The different dots stand for the response of the device upon exposure to different concentrations of the different VOCs, namely volatile organic compounds, in both 5% and 40% relative humidity. The accuracy level of discrimination in this case was 95%. This figure represents the ability of the array of pH-based field effect transistors to separate the analytes into groups and into sub-members of each group. After separating between aromatic and non-aromatic groups in the previous slide, further subclassification is made to differentiate between the polar and non-polar analytes and their subgroups. In each separation, a combination of different features and sensors is used and a model is created. Figure A on the screen shows discriminant factor analysis separating the polar material from the non-polar material. The accuracy level of the discrimination in this case was 80%. Figure B shows discriminant factor analysis separating the aromatic material, namely between mesethylene, styrene, ethylbenzene, and toluene, and in this case the accuracy level of the discrimination between these groups was 75%. In Figure C, you can see DFA results separating the non-polar volatile organic compounds, namely between hexane, octane, and decan, and the accuracy level of the discrimination between these groups was 75%. Now, we can see that Figure D shows DFA results separating the polar materials, namely between octanol and decanol, and the accuracy level of this discrimination between these two groups was 79%. The different dots are shown on the screen or on those graphs stand for the response of the device upon exposure to different concentrations of the different volatile organic compounds in both 5% and 40% relative humidity. Altogether, these results demonstrate the visibility of the pH-based field effect transistors for volatile organic compound sensing applications in humid atmospheres. The ability to extract multiple electrical features as well as multiple signal features from each pH-based field effect transistor provides a reservoir of sensing signal that allows discrimination between aromatic and non-aromatic volatile organic compounds, discrimination between polar and non-polar aromatic compounds, and identification of specific volatile organic compounds within the subgroups at both low and high relative humidity levels. We reach now the end of class number 9, session number 4. Thank you.